This question says a scientist tests trout from a lake in an active geothermal region to see if they are being contaminated with methyl mercury, a poison that builds up in the body. The World Health Organization's safe limit is considered to be 500 ppb, which is parts per billion. Okay, so that's the safe limit. So anything more than that would be unsafe. A scientist tests 20 fish and finds that the average, so this is your mean, which is your average, methyl mercury level of 378 ppb. Okay, so that's your mean. And then you got your standard deviation from the mean to be 127, and the total number of fish, you're saying there's 20 fish in total. The first question asks us what proportion of fish will be over 500 ppb. So basically for this one here, what we have is we have a normal distribution. Let's quickly draw our normal distribution. Now remember, the normal distribution with the graphics calculator, it depends on how you're looking at it. Now we know that this is the mean and this is like a number line, and we know that this should be at, in this case we can see the mean was 378, right? So we take the 378 and we place it in the middle of our normal distribution. Then we say in the safe limit is 500 ppb, so this is actually ppb, and the safe limit is 500. Now we know 500 is going to lie on the right hand side somewhere over here. And it says here the scientist tests 20 fish and finds that that's the average. What proportion of fish will be over 500, which is a recommended limit? We want to find out what is that probability over there. So what's the probability that the number of fish X is greater than 500? Is the question. We then have to calculate this using our calculator, or we could use our normal distribution, standardized normal distribution. So what we're going to do is we're going to use the Z tables, right? So if I have to use a standardized normal distribution, when you standardize normal distribution, you are bringing the normal distribution to a mean of 0 and a standard deviation of 1. In order to do that, you end up with a coded and exactly coded form of the 500, which is your Z value. And then the Z value, you read off this from the table, which is your probability. So at the moment, to get this Z value, we use this coding, which is Z equals X minus mu over sigma. And at the moment, we have 500 minus 378, and we're dividing it by our standard deviation, which was given as 127 in our question. We put this on a calculator and we end up with the probability 0.9, sorry, end up with the Z value, not the probability, 0.9606. We can stop 06, and you can see that it's on the right hand side of 0. So this value over here is 0.96. We have basically standardized, we've converted the 500 into 0.96 relative to if we had to change the mean from 378 to 0. This is called standardizing, right? So this is standardized normal distribution. Now we have to use our tables, and we're going to read off the Z value. So we're going to find this Z value on the axes of our tables. We're going to have a look on the axes, and we're going to read off the probability inside there. This is the standard normal distribution that you're given at the back of your book. Now you're looking at 0.9603 on your Z table. So if you look at the Z table, they're covering the area from 0 to Z. We're saying that this number is 0.96. So whatever answer you get over here in this Z table, this probability is going to be that proportion. Now remember, in our graph, we don't want that part. We are going to get that from the table. So the table is going to give us this. Alright, it's going to give us that part over there. So what we have to do is we have to take 50% and minus it from whatever we get in our table. to get our final answer. So we're going to read off 0.9603 now. Let's go to our axes. So 0.9 is over there, 0.96, 0.9603. So 0.96 is over here. Okay, 0.96, and we have to round it to 3 significant figures. We're going to get 0.961. If I have 0.961, I'm going to have the following: 0.6, 0.961, 0.96. And then what we do over here is we adding 1. So there's the 1 over there, 0.961. We then trace down again, and we add 3 onto the 15. We add 3 onto the 15 to get 0.3318. Just double check that. It's going to be 0.3318. So that Z value over there gives us the proportion. I'm going to just redraw it from the table. Remember, this particular table, they'll always indicate at the top of the table what area you're actually finding. In this particular instance, we found that if we read off 0.961, we add 3 onto 0.3315, and we end up with 0.3315 plus 3 at the end, 0.003, gives us 0.3318. That's going to be the probability of it being between 0 and the Z value 0.961. Now we don't want that one. We want to find this is where the answer lies. So therefore we take 0.5, which is 50% of the data, because that's 50% over there. We take 0.5 in our final answer. We're going to minus 0.3318, and we'll end up with 0.1682. And this is using Z tables. All right. Now, one thing you notice, because of the symmetrical nature of the normal distribution, is that if you had to calculate this on the other side with a negative 0.961 for whatever reason, it would produce the same probability as this side. Alright, so you'll notice in your answer there, probability x is less than 500. They simply calculated the same probability but using the other end of it. Okay. And that's your final answer there for question 1A. B says, alright, question 1B says, what range of methyl mercury levels would include the middle 90% of all trout in the lake? Alright, so this one here, what they're giving us the probability. So they're saying that the middle 90% means that we have to calculate the mean. Well, we're given the mean, which is 378, and we know that we want to get to 90% for our area. Okay, so which means we'll have 5% on either side. Now, so this is 90%. Then these two have to be 5% each. So that means we want to calculate, if we use our normal table, if I just redraw it, just looking at the normal tables that we have at the back of our textbook. The normal tables over there, we basically saying that if this is 50% and that's 5%, we know that this is 45%. So what will this Z value be if this was a standardized normal distribution and that area was 45%? We would then go to 0.45, and 0.45 is approximately around here, so it'll be 0.04, and we're going to add 5 onto it. So if I add 5, I've got to add 5 also onto my Z value, so it's going to become 0.055. Alright, let me just go back down again. So what you have here is you got 0.45, we're looking for 0.45, so I'll go 0.45, 0.45, there, 0.449, 0.45 will lie between those two numbers. So we're looking at the Z value 1.64, and then we're going to make this by adding 0.0005 to it, by adding 5 at the end of the last part of it, the decimal, we would then add 5 on top of z value, so 1.645, 1.645. And that would be the specific z value that would lie here. Now we know that using the standardized normal distribution, we have x minus the mean over the standard deviation. This is the standardized normal distribution formula. We know the z value now, so this is why they call it the inverse normal distribution, because you know the z value, you don't necessarily want it. And this is inverse normal, and this is equal to my x value, which is what you want to find now. Okay, so you want to know what is that x value going to be. So that x value, you just leave it in your equation. Your mean is 378, and your standard deviation is still 127. You now have to multiply this and add 378. So 1.645, we would multiply 127, and we would plus 378 to get that specific value that will ensure a 5% probability on the right hand side of the normal curve. And you will end up with 586.92 is that specific x value. So that means if this is 586.92, the distance this way will be the same distance this way. So if we subtract these two, we'll end up with that value over there. And when we subtract it, we'll end up with 169.1. Alright. And that's our answer. So therefore, the range will be between x1, and we can call this x2. So x1 will be that. x2 will be equal to 586.9 minus 378, which is 169.1. 169.1 to be the second value, and that will be the range between those two values. Question C says, a nearby lake recorded a mean methyl mercury level of 392 ppb. So that's a new mean. So we got a new mean now in question C of 392. And the standard deviation is also changed to 88. So suddenly we're saying that the normal curve is going to be a bit more steeper, because it's definitely got a smaller standard deviation. So in order to cover the same probability, we have to then say that it's going to be steeper, falling away to near zero more quickly. Alright, it's a smaller standard deviation. Describe the differences in the distribution of mercury in the fish compared to the first lake, and particularly how that relates to those with extremely high levels of mercury. So let's have a quick drawing of this. What we have is, initially we know that our mean was at 378 and the standard deviation was given at 127. That means if you add 127 and you subtract 127 from 378 on either side, you get to one standard deviation. Alright, I'm going to call it sigma 1 on either side. If you add 2 times the standard deviation, remember that's plus or minus 127. Now we're saying that this mean has now changed to 392, which is, let's say it's around here somewhere, right? 392. But the standard deviation is 80 and 80 before it reaches that same probability on the standard normal curve. So what we're saying over here is that the entire graph has to cover one standard deviation in a shorter space of time on the x horizontal value, horizontal x-axis. So we're saying that it's going to be steeper in general. So the first idea behind this is that the second graph will be much steeper. And the reason for this is because it has a smaller standard deviation. So if you have a smaller standard deviation, suddenly your normal curve becomes steeper. Alright, although in the second lake the maximum will be at the higher mean 392 and not 378 because it has less spread, due to lower standard deviation, it will still have fewer fish with extremely high values. So what happens is you got the original curve, and if I just draw them overlapping on each other, then the next one is looking like that. Why will you have fewer fish? Let's suppose I take some kind of random x value over here, a normal curve, this is my mean. You can see that the proportion for the original curve, there's a much larger area versus the new steeper curve. Okay, you can see that that's going to be less. So we say there will be fewer fish, therefore there will be fewer fish with extremely